Welcome to this lecture 17, Advanced Introduction to Machine Learning course. Last time we looked at some applications of natural language processing and some of the state-of-the-art models in NLP, specifically transformers. So it's a very exciting field right now. I mean, it has been exciting even in the past decade, but it's even more exciting that natural language processing has kind of become democratized. Almost everyone is talking about chatbots and chat GPT and what they can do for you on a daily basis. Like there's conversations on how chat GPT can be used for this or chat GPT can be used for that. Um, you know, chat GPT can help you write essays in school. And so then there's discussions around, how do we learn and how do we you may have to change the curriculum in schools because a lot of the comprehension tasks can be done by ChatGPT, which is freely available. So, what really is then learning for humans? There's like very interesting tangential discussions that happen around this new tech, and there's so many more variations of ChatGPT, and like there's like large language models that are getting released. I think Meta recently released Llama, and Google's released its own version, BART, and so there's so many different versions coming out, and these are just the pre-trained models, right? The fine-tuning of these or how they actually get used in different niche markets, I think that's going to be like $1 billion business or more, right? So we're going to see a lot of startups coming up that are going to be centered around Chat GPT and its use cases. So it's a very fascinating field to be in. And if you had any interview that involved Chat GPT, one of the most fundamental questions that you'll get asked is on transformers. So today we'll focus on understanding transformers a little bit more. I think last time we went a little bit quickly. So today we'll spend a little bit more time understanding what exactly is happening there. And I encourage you to ask questions on any aspect of this because that will actually support your learning rather than me just doing all the talking. So anytime, feel free to stop and ask questions. And yeah, it's a very fascinating field, and I believe there are many startups already that are centered around these around transformers and other natural language applications. So, and then obviously you have the other side, which is vision. So you have image data and text data. So if you look at data, there's images, text, images, text. So vision has its own set of startups and companies that are trying to leverage the technology in vision. So yeah, so we'll go a little bit deeper into transformers today. And we'll also talk about attention in the context of transformer or other models as well. And we'll continue with the demo that we started last time. I think there was one more notebook that we didn't cover, so we'll go through that as well. So, and you'll get to use transformers. I think you're encouraged to use transformers for the second mini project that is coming up. So you can actually work with it and see how it delivers results in comparison to a traditional or a simpler natural language processing model. Okay, so we spoke about evolution of architectures last time, starting from perceptron, feed-forward neural network, being a bunch of neurons and a bunch of perceptrons, right, or a bunch of neurons put together. Then we said RNN introduced sequence and dealing with sequence structure. And one of the most natural applications of sequence is language, right? Because language is a sequence of words, language is a sequence of characters or subwords or whatever, however you want to represent language. So sequence came up first for language models. We see CNNs more for vision. We don't see, RNNs or sequence models for vision. But for language, we see that sequence is such an important thing to model. So RNN was one of the first models, and it had its drawbacks. We spoke about a couple of them, which is vanishing gradients and exploding gradients. And we said this is connected to the multiplicative nature of how you go from one cell to the other. you're taking a state here and then you're multiplying it with some weight matrix and getting here. You multiply it with some other weight matrix and you keep going. Actually, these weight matrix multiplications are kind of similar. So that's what is represented here. You learn one set of weights and you keep repeating them from one, from one character to the other. So the input is changing, but the parameters here are the same. So the parameters are shared across the RNN. So that's how you see this kind of a circular representation, that you just keep cycling through the input outputs, but the weights that you learn are for one particular feed forward setup. So you can think of RNN as a bunch of feed forward, right? So RNN is chaining feed forward networks. So again, you saw from perceptron, you chain perceptrons, you get feed forward. You chain feed forward, you got RNN. So again, a bigger version. And then LSTM resolved some of the issues with RNN, which is exploding gradients and vanishing gradients. So you have a long-term cell state, and then you have a short-term cell state. So we spoke about this as well. Then we spoke about attention a little bit as being able to, and in LSTM, attention is a lot about looking into the input to while you are looking at the output. So when you are generating the output, you ask a question, you want to give an answer. So the input is, let's say, question, and the output is an answer. Or you can have other inputs, right? Your input is a document, and input is a document, output is the summary of the document. So all of this is text: question, answer, text, document, summary, text. So when I'm generating the output using this recurrence relationship, I want to look at the input to inform me about the output. So I don't want to just get a state from the input. I want to be able to look at the input tokens and then pay attention and then generate the output. So keeping the input in mind, I generate the output, right? So that concept mathematically is attention. As you generate your output, as you generate the next word, next word, next word, keep paying attention to the input. Don't forget about the input, right? So that's basically what attention is, the main concept. So you can think of it this way. So you have, let's say, input tokens here. And then let's say this is your output. So maybe let's say input is, do you like NLP? And the output is, yes, I do like, and so on, right? So the idea of attention is I'm generating this one at a time. And this is true even right now, like with ChatGPT. Even though you type in something and it generates things instantaneously, it is generating one token at a time, right? And it is not generating it in one shot, right? Like the output is all there. It's going through it in a sequence. So attention here would be, and this is called cross attention, is, let's say, I've already gone through this. I've generated a yes. I want to generate I. When I want to generate I, I'm going to pay attention to my input and take in feedback from the input on which word, what have I answered so far and what is left to be answered? In this case, question answering. Or if it is translation, what have I translated so far and what is left to be translated? So I look to the input to help me understand what have I answered so far. For instance, I've said yes. So the question is kind of answered here, but yes for what? I haven't answered what is the yes for. The yes is for NLP, right? So I do want to mention NLP, so that's coming up. So as I go to this token, it's going to pay more attention to NLP and less attention to any other words, and force the model to generate NLP. So you have an attention mechanism that you use during training that can help you understand which parts of the input token are you referring to as you're generating the output. So that's the concept of attention, but it's definitely a little bit abstract, but it's also called scale dot product attention. So you take a dot product. So for instance, here I'm taking a dot product between something here and then something here, right? And then I'm generating probabilities for these edges. The probability is telling me which of the input tokens I'm placing more attention on, and that attention changes as you go through the input, right? So at the beginning, maybe my attention is more on the question mark because I want to say yes, yeah, that's the question. Yes, the answer is yes. So I pay attention there. But as I keep going, I pay attention to other aspects of the input that are more relevant. So that's the idea of attention. I think there are some good illustrations for it. Maybe I'll share it next in the next lecture. We can take a look at how attention actually changes as you go from input to output. Okay, so we have attention, and then transformer is a nice extension of LSTM with attention. And so we'll focus on this a little bit more today, break it down, understand each part, and see, how it all makes sense. Yeah, so transformer is a bigger and better and advanced version of LSTM with attention, and it solves some of the issues that LSTM had. For instance, LSTM would still hallucinate words when it generates output, or LSTM doesn't have a very large long-range dependency, which transformers are able to bring in. And LSTM doesn't do as good a job on understanding a sentence as transformer would. So these are some of the drawbacks that transformer is able to resolve, right? So one is better encoding of sentence. So here's the thing. We've looked at word embeddings with word2vec and glove. We've looked at word embeddings. We had an assignment on it. That's an individual word. That's easy because let's say you have a skipgram model or something. That's easier to understand. And that's not with context. There's no context to it. Like you get a word embedding, like cool will have the same word embedding in any context. Like if I say, hey, this place is very cool, do you mean the temperature is cool or do you mean you like this place? So I need to know what came before cool to understand if you're referring to the temperature or you're referring to the coolness factor. But if you look at glove embedding for cool, do you have different embeddings for different sentences? No, right? So glove embedding is non-contextual embedding. But if you get an embedding for cool that understands the context, that's a contextual embedding. So here, transformers can give you contextual embeddings, right? So that's one of the key advantages of using transform. And here we're not even looking at a single word, we're looking at the whole sentence. So you can get an embedding for the whole sentence from a transformer, not just individual words and tokens. And also you get better embeddings for an individual token and understand the context. So like just to make it more clear. So sentence one, I like this place. It's really cool. In the second place, second sentence, can you turn on the heat? It's really cool here. Okay, so what do you notice between these two examples, right? Both have it's really cool. So it's not just one word. Both of them have three words that are in common and basically two sentences that are really close to each other. But what came before that sentence gave the context to know what cool really means here or here. In the first case, cool refers to temperature. And then the second case, it refers to, sorry, this is temperature. And then this is, so the coolness factor. So you can see even with a single sentence, you may not get the full context. You may need to look at sentences before. But transformers, they can handle one sentence, two sentences, they can handle a paragraph, but they do have a limit. You cannot handle more than 500 tokens. So the people who came up with transformers notice that when they do training, the performance degrades after 500 tokens. So tokens here would be subwords. It could be a word, but it could be a part of a word. So base words, root words that the model kind of did the data processing, right? I think for BERT, we have word piece tokenization. So words or subwords are used as tokens. So you can handle up to 500 of those tokens. So that could span a paragraph or two easily, right? So you can get context from paragraphs to say what exactly, like if you ask, what does cool mean here? A transformer would be able to say what cool means here better than, let's say, a sentence-based embedding or a glove embedding for cool, which would completely fail the task. So preserving context is something that transformer is good at, right? So better encoding of sentence, preserving context. Yeah, and less issues with hallucinating words and things like that.
Could you clarify what you mean by hallucinating?
Yeah, hallucination is something that some of the earlier language models suffered from. So, like especially like RNN hallucination issues. So it would say something like, "I like this place," and it's hallucinating these words, filling it in when it's not needed. For whatever reason, it's not able to construct a grammatical clean sentence like ChatGPT is. So if you were to use RNN, you have these issues. LSTM might still have some of these issues, uh, but to a lesser extent, because it has this long-term cell state that is not present in RNN. And transformers, as you can see, like the GPT models, do not have hallucination issues in English sentence construction, but they have hallucination of facts and reasoning. So you say, can you type me up a LinkedIn profile, and then ChatGPT would be like, here's your LinkedIn profile typed up, and it could hallucinate a lot of things in there in terms of facts, but in terms of quality of sentence construction and everything, it's like flawless. So even getting that right was an issue with some of the earlier models in natural language. So only in the last like 6-7 years with transformers have we been able to even get sentences right, sentence generation right in natural language processing. Yeah, so generation had hallucination issues. Hallucination is one issue. You also have grammaticality issues, like periods appearing in random places, or not using the right punctuation. All sorts of other issues could come up with these simpler models because they were not looking at the full context. They didn't have good encoding representations, um, and so on. So there were multiple issues with these earlier models. Um, the other advantage of transformers is they apply to almost every NLP task. So previously in traditional natural language processing, you say machine translation, okay, I'm going to use this model. And then people would do research in that area, develop good models for language translation, and say, this is the state of the art, this is the best model. Or someone's working on sentiment classification. They have their own models. And then someone's working on something else. And they may or may not share models. They might be independent. But after the advent of transformer, almost every single state of the art model has some backing on transformer, because the transformer is understanding language really well. Once you understand language, then when you ask me questions, I can tell you the answer because I understand language. So understanding language became a fundamental thing that transformers were really good at. And that's coming from the pre-training of the transformer on millions of documents on Wikipedia corpus or other book corpuses. So when the transformer is seeing like document after document, book after book, in its training, it has seen almost all kinds of contexts concerning English sentence construction. So it's gotten really good at it. And you need tons of training data, which it is using, but you also need a powerful model, which the transformer is. So combine powerful models with lots of training data, you can get something that understands language well. So these are the transformers are one of the fundamental models in the large language model class. So LLMs. So you hear about LLMs, large language models. And then so people even the ones that are coming up more recently, they might be some variations on transformer, right? Trained this way or that way. But understanding language became the fundamental thing that the transformers were wanting to solve. And once they did that, you can take its understanding and build another feed-forward network on top of it, build another classifier on top of it, and you get good results. So it became like, okay, break up your task into pre-training, which you already have. Someone has already spent hundreds of thousands of dollars to train a transformer model on the cloud, and they've generated a beautiful transformer model. Now fine tune it. That's the thing I would want to do for my task, is fine tune it, not have to pre-train it, which is more cost efficient. And I'm kind of standing on the shoulder of giants, right? So transformer is a giant. It understands language much better than I can do on my own with my own training. Like I might have a limited set of training data. Transformer is going through millions and millions of documents and hundreds of thousands of books. I can't match that kind of data and complexity. So I will leave all of that language model understanding to transformers, but I'll use it as a starting point. So any weights that you learn here, right? So let's say I learned all these weight matrices inside here. I'm going to use that as a starting point for my training on maybe my 10,000 size data set, and fine tune these weights a little bit as much as needed so that I perform well on my task. So I'm not going to like do training from scratch. So that is fine tuning. Initiate your transformer model with the weights that were learned in this pre-training. Don't mess with it so much, just initiate it. See if you're on your limited training data, your model wants to change any of those things. Great. If it doesn't, no worries. And sometimes you don't even do that. You just start here. Maybe start here, you get a representation here or here, right? So you have a sentence, and then this is a sentence encoding. So sometimes I start here. I just skip the whole transformer layer. I say pass my sentence through the transformer, get an encoding, see if I can use this into another classifier for sentiment analysis, or for token analysis, or token classification, or question answering. And then it turns out if you did it that way, you do a good job. You do a great job than if you were to train a model from scratch on your own. So leveraging transformer as a pre-training model has become kind of the state of the art. And it has, like you've seen like paper after paper where it's beating a lot of benchmarks. So that's the power of large language models, is it is leveraging tons of data and tons of training, tons of compute time, and tons of optimization, which I may not be able to do as an individual on my own. So that's why big companies invest in this, because they have the resources to be able to do training, pre-training of large language models, right? But what happens downstream is important for the end task. So fine-tuning is an important step. So even for mini project 2, we'll only be doing fine-tuning. We're not going to be doing any kind of training on the base model. So you just load the model and then fine-tune it. And you might add more layers on top of the existing model, and then those will be trained from scratch. But any of the transformer components are only fine-tuned, right? So that's how it works. Any questions or thoughts on this so far?
So I think I misheard you. The last couple minutes, I thought that started with, this is the problem with transformers. Was that wrong, or were we describing a problem that transformers have brought to machine learning?
What problem were we talking about? Sorry.
That's what I was trying to figure out for the last couple minutes.
Uh,
Is it a problem? I'll rephrase it this way. Is it a problem that everything is built on this?
no, it's not a problem. It is a challenge to pre-train a transformer on your own. So you kind of outsource it to people who have already done the job. And so when you go to Hugging Face, for example, you almost never do pre-training. You just load an existing BERT model or a BART model or something, and then fine-tune it. So it's a challenge, it's not a problem. And it's a challenge that people with resources will take up, but we don't have to worry about it.
Okay, so the problem is someone has to ruin the environment by training it.
Well, yeah, and if not many people are doing it, we're good. So,
yeah, okay.
So thankfully, a million people are not doing pre-training on transformers. Maybe a few thousand people are doing it. So that way, in terms of the environmental impact, we're good. But if everyone was doing pre-training, then we would have a big issue, right? So thankfully, it all works out. So you can do as much fine-tuning as you want. Everyone can do fine-tuning, and we're not going to be impacting the environment as much.
All right, thanks.
Yeah. No, that was one. And also I was saying that transformers resolve the issues that LSTM and RNNs have with hallucination, with grammaticality, and not having enough context, not getting enough context into the representation. Like the classic example is this one. So LSTM may not be able to understand what cool here really represents as well as transformer would. So that's those are some of the wins that we get through transformer. Do transformer have limitations? Well, with ChatGPT as a use case, you can see that ChatGPT can do well with sentence construction, but not so well with reasoning and fact checking. So these are still language models, which means they understand language. They may not understand how to reason. They may not understand how to. They are very good at understanding patterns in language that or books they've seen before to kind of mimic it or parrot it in the question that you're asking. If they've seen something similar in the past, they might go back to that and then share something appropriate. But if you really start reasoning with ChatGPT, it'll fail after some time. So it's easy to ask, go into some dark areas, and then ChatGPT is like, I don't know what to say here. So this is an emerging area where people are saying that, oh, these are language models. They're not meant to do, multiply two numbers. Like people are asking, can you multiply these two numbers? And they say, oh, ChatGPT doesn't work. Well, it's not built to multiply two numbers. It's built to, generate sentences and generate responses to questions. But it is not very good at reasoning tasks. So this is a new area where people are saying we're going to take a large language model and augment it with other models that are good at specific tasks like calculations. Let's outsource it to some other, like how hard is it to build a calculator? It's one of the easiest things, right? You want to multiply two numbers. That's one of the easiest things. Like anyone can write a code for it. Why is ChatGPT not doing it? Because it's not built for it. So you're asking something really huge to do something very specific, which it's not built for. It's not going to do it as well. So augmented language models is like the next paradigm after large language models that's kind of coming up on the market.
Professor, I have a question. It's real quick.
Sure.
For instance, ChatGPT, how do they clean? Well, it's said that large language models are very toxic at the beginning. So how do they clean that? How do they remove all those bad words? Do they train like another ChatGPT train only for toxifier, and then it starts like a GAN process, just like make some sort of cleanup process? Is that the way, or?
Yeah. So they have filters, I believe, that understand if the question being asked is offensive. So don't engage so much with an offensive question, or if your response is offensive. So if you want to remove bias, you have to detect bias. So they will have bias models that can detect bias. And then that's sitting on top of, it's just like, let's say I got emotional, okay? And you ask me, how's my day going? And I'm going to be like, yeah, it could have been better. I think you're being rude right now by asking me how my day is when it's already not going well. I'm right now emotional. I'm right now stressed. So then if I realize it, I'm going to check that and then say, maybe I'll talk to you later, right? So we are able to correct ourselves when we respond in conversations, or we are self-aware of what's happening when we speak to people, right? So bringing the same kind of concept to ChatGPT is how, is one way to remove bias in both input, detecting bias in input, and also in the output. So we'll go through filters and make sure you're not saying something offensive, even if you've seen something before in the training data. So how can you make sure your training data is clean? That's a hard problem, right? There is bias that you can detect, and there's bias that you cannot detect. Like there could be no offensive words in the training data, but it could be offensive when you look at it as a whole, right?
Yeah.
Like we use some phrases that are offensive, but any single word in it is not offensive.
But are filters good enough to make sure that large language models are not toxic?
I think ChatGPT, as far as I understand, does a good job at it. But there are other ones that are coming up that are still, working on it. So yeah, I don't know about Bing AI and how good it is, but some of the new ones might need some more tinkering. So the other way to do it is you have a generic bias model that's kind of going to keep filtering things out, and because for every input, every time I want to generate a new sentence, I have multiple options that ChatGPT can pick from. So it can score it based on relevance and bias and pick the one that makes the most fits well and then put it in. So that's like being proactive on bias, but there could be bias that goes undetected. And then if it surfaces somewhere, then people are able to take that as input and then make changes. Or here's another thing that can be done. You adversarially pass in inputs that are biased or offensive and make ChatGPT be non-offensive. So you train ChatGPT like on a data set where the input is offensive, but the output should not be offensive. Or so people, I'm very sure OpenAI is actually collecting or has collected lots of such data sets and then fine-tuned ChatGPT on these data sets. So you pre-train and then you fine-tune again. And then so you make sure that your responses are better. Yeah, so it's not like one-shot training and then we're using that version of ChatGPT. It has gone through several post-processing steps, and it might still keep going through more of that before we get to actually get a less biased model.
Thank you.
Yeah, so explicit bias is easy to detect and easy to filter out. Implicit bias that even we find that we have to pay attention to before we understand that that's a bias is also hard for ChatGPT, because the training data consists implicit bias. So then it's going to reflect in the responses as well. And it could be something very innocent as like I saw a post on LinkedIn where someone asked, so this is Rob. What would Rob like to work on? And then ChatGPT would be like, he would like to work on coding, or he would like to work on this or that. And then you change the gender, and then you get a different set of responses. And some of that may or may not reflect bias, right? So it's a simple, innocent question, but if you see there is a disparity in the responses, those are some of the biases implicitly present in the training data. Because ChatGPT has seen more of these associations between this gender and the kind of work they do, it's going to reflect that in the response as well. So, yeah, people, yeah, it's a good question. Yeah, I would encourage playing around with ChatGPT, and people also try to be adversarial with ChatGPT, try to force it to do something, you know, get it into a corner, and then it then say, got you right now you're not, so those situations happen less often in practice, but you still want to keep improving and make sure you don't have you reduce the bias as much as possible, right? But yeah, I think it cannot be one model. It has to be a model plus a lot of supplementary models to filter, screen, and improve on it. So ChatGPT also has reinforcement learning with human feedback to kind of fine tune its responses on top of GPT. So it already has two main models sitting in there, but it probably also has other supplementary models to improve the quality of the output.
Professor, you mentioned that ChatGPT uses reinforcement learning with as a transformer. How close are we to artificial or general artificial intelligence?
Yeah, I think we have to define what that is first, right? So,
Well, that's the debate on how to even define it.
yeah. Well, so it used to be that people would say, if you can have a machine that speaks like a human, then that is artificial intelligence. Anyone know what the name of this challenge was?
Turing test.
Turing test, right?
Yeah.
So Turing test was the big aha moment, right, for AI, where you could and right now you look at ChatGPT responses and you say, oh yeah, that's something I would have written or someone else would have written. So seems like ChatGPT is passing the Turing test for most of it. But that's not enough, because now we are looking at reasoning. So reasoning is the next paradigm. So if we can have a test on reasoning, then maybe that's the next dimension. And
So maybe like common sense reasoning.
common sense reasoning, and
Yeah.
also evolutionary reasoning. Like if you look at humans, we don't need too much of examples, training data. Every time you look, let's say you go to a new location, you travel to a new location, you're like, I need training data to know how to talk to people here. We don't do that. We leverage our past experience, and maybe in a new country, you have to observe a few other rules and you pick it up quickly. You don't need like thousands of training data to understand the new city or new place. And even if you don't understand the language in a new country, you can observe very quickly some behavioral patterns and then say, I'll follow these things, right? Maybe there's some social customs are different in a new country, and I'll pick it up with a few examples, right?
Yeah. You can call that transfer learning also. So we have these techniques that.
Yeah, you can, but also you go back to your own experience. We go back to our own experience, and we have some really good common sense built in, or we build it over time. As so the idea is probably the same for general artificial intelligence. Is it's looking at a lot of data continuously. It's having its own life experience, and that is shaping it up to be more intelligent. So we're not there yet. So that's probably the next paradigm is what is so I want to say, what is a life experience for a GPT? What does that even mean, right? And how can it reason from a few examples? So yeah, you never know, but I think we are on the way. We have to crack the reasoning part. The community has to crack the reasoning and common sense part, and I think then we'll probably have a really amazing bot that we can use for many tasks down the road. So maybe another decade, 2030, we should ask this question again on where we are at. Yeah. All right. So Great. But this is a very fascinating area, and do feel free to spend extra time on this because it's totally worth it, understanding what's going on here. Okay, so we'll now go a little bit more into the technical details and understand some of the architectures here and understand their applications, understand some of the ins and outs at a higher level, right? At the low level, understanding transformer, you have to work through the math and everything. We'll skip that part. I'll just mention a little bit higher level, but if you're interested, there are some blogs on transformers that can go much deeper into what it actually does, right? You can look it up. So BERT is one of the most fundamental models, and we'll look at this. There is also BART and there is GPT. So these are three fundamental models, right? Okay, we spoke about this last time. Transformer. Yes. Okay. So transformer has encoder, decoder. So we spoke about this last time. If you only use encoder, that's BERT plus its variants. Right? Only encoder. If you only use decoder, that's GPT and its variants. So you see GPT, GPT-2, GPT-3, and all of that. It's only using decoder. It's not using the encoder part. And then you have both encoder and decoder. So these are models like BART, DeFi, and so on. So BART is especially very popular. So why use only encoder or only decoder or both? So encoder is what we spoke about. Can you understand the context of the word cool in a set of sentences? I want to encode that body of text. And once I encode it well, I understand the context, I go back and forth, I look at the sentence as a whole. Like when someone gives you a sentence and says, what does this mean? You're going to look at the whole sentence, right? You're not just going to focus on the word. So looking at the whole sentence is the job of the encoder and understanding. And so we call that bidirectional. So BERT, this stands for bidirectional encoding. So you look at both the directions from where the token is, you look at both sides and say, okay, this is what cool really means. So that's the job of the encoder. It gives you good representation for a token looking at the sentence as a whole or sentences as a whole. So it gives you good representations for downstream learning. One second. Okay, so one other conceptual thing about BERT and how embeddings happen in BERT, which was a new thing. I mean, it was part of transformers as well, but BERT also added this thing called segment embeddings. Is how do you know where in the sentence a dog is present, right? If a dog comes towards the end of a sentence or it's in the beginning of the sentence, would it make a difference, right? So would the positioning of a word in a sentence make a difference to its embedding? So, and it turns out it does, right? So if in some of the contexts where you use the word, can play a role in what the context is and the meaning is, right? So for example, if I say, I don't know if I would like to do this, don't is coming at the very beginning, that means you have a negative sentiment. But if don't comes, at a later point, it might have a different context. So depending on where a word shows up, the embedding and the meaning of that word might change. So that's where the position embedding comes in. So every token or every word in the input gets an embedding, right? So that's what we call token embeddings. So this is just like let's say glove. So this is like glove. Okay, if you had an embed, if you have the word he, this is the embedding for he. This is if you have dog, this is embedding for dog. So that's basic. But how do you incorporate context and position? That's where position embedding comes in. So this is the new thing about how to take care of the sequence aspect. So position embedding includes the position of the word. And then there's also segment embedding. If you have more than one sentence, then which segment does the word belong to, the first segment or the second segment? So let's say two segments here. So you have EA and EB. So two sentences, your input has two sentences, then you want to include the sentence in which the word belongs. So maybe the word dog belongs to this first sentence and this dog belongs to the second sentence. So that can, that may also be important. So token embeddings, segment embeddings, and position embeddings are summed up, and then you get the input embedding. So input embedding is basically a sum of all of this, right? And the input itself looks like this. There's a start token, and then there is separator token for sentence separation. And there's also end token, which could also be the same as separator. So this is to help the model understand, this is where the sentence starts. This is where this sentence ends, and this is where the next sentence starts. And this is where the whole input ends. So giving indicators for the model helps the model know what to do, right? Also, these could be subwords. So you see here. So the sentence is, my dog is cute. He likes playing. That's a sentence. But if you look at the tokenization, my dog is cute, they're all words, but he likes playing. So the ing is now a subword because play shows up more often than playing. So the model would be like, let's use play as a token, and then ing also shows up more than playing. So let's use ing as a token. So the representation of words would be through these subwords. That may also be words. That is a tokenization process. So this is a tokenized input with subwords. And then this gets passed in as input here. And so for each of these tokens, I get, so at the end of going through the encoder, for each of these tokens, I get an embedding. And that's the embedding that is contextual, rich, and deep, right? And in terms of your actual, let's say the Hugging Face model, or when you actually go and implement it, you'll see that you know everything's a number. So you'll get an index. So you'll get an index for this token, index for this token, and so on. So when the model sees the index, it'll be like, oh, this is the index. So let's pass in the position embedding here, and the segment embedding, and the token embedding. So based on the index, it's able to put together embeddings and then pass that in as input. And inputs to the encoder or decoder are tensors, right? At the end of the day, they're tensor objects. And then the tensor gets modified. So it's all tensor arithmetic matrix or tensor vector multiplication, tensor matrix multiplication that's happening inside the encoder and decoder. And then the output is also a tensor, but you know what that tensor corresponds to. For instance, I get a tensor here. I know that tensor corresponds to the word is. So that's the embedding of is. So you know what the embedding is. And then this embedding, the final embeddings are what get used downstream tasks. Okay. So a little bit about tokenization and representation of the input here. And like we spoke about last time, there are two tasks that BERT is trained on, MAST LM and next sentence prediction. And these are self-supervised, right? Self-supervised learning. We spoke about data set as well, English Wikipedia and book corpus documents. Skip this. Yeah, we spoke about question answering and summarization that can be done through BERT. So transformers can also be applied to vision. So CNN is the more popular model for images. But if you were to apply transformers, you can segment the image, right, into a patches. So each of this is a patch, and then you do linear projection on these patches, and then you add a position embedding. So just like we add a position embedding to the word token embedding, you can add a position embedding to the image embedding. Image embedding is going to be some tensor or matrix. So it's easy to add a position embedding to that. And then pass it through the encoder. Just like we would pass in sentences, you now pass in image patches. So then it will do attention, just like we did attention on sentences, you can do attention on the image. And it will understand the image better. Once you understand the image better, you can ask questions like, what does this image represent? And then it would give you an image, it would give you a caption for an image. So that would be the decoder part that will give you the caption. The encoder takes in the image and then gives you image representation. Okay, so the nice thing about encoder-decoder architecture is you can mix and match. So when you use transformer for vision, it's called a vision transformer. So you might have heard of vision transformer. So it's just the application of transformer, but to an image input. Okay. All right. The other thing I want to talk about is just to compare BERT, BART, and GPT. So in BERT, if you look at how it's trained, you have tokens, but you mask certain tokens, right? So this is mask. And whatever you mask, you try to predict. So that's how BERT is trained. I'll randomly mask certain tokens, see if you can predict them. So that becomes a classification problem, multi-class classification for every single mask token. So we know we use cross entropy for classification. So you'll have a sum of cross entropies across the mask token as your loss function for the BERT model. Right. Now let's look at GPT. GPT tokens are predicted autoregressively, right? But you can only condition on the left side, so you cannot do bidirectional interactions. So this is simple. You pass in a start token, you want to generate, let's say A, you pass in A, you generate B. So here again, this is cross entropy because you know what token you want to generate. So you apply a cross entropy loss across all the tokens you want to generate. So that's BERT, so that's GPT. And then BART is bidirectional because you have an encoder and you have a decoder. Sorry, BART has encoder-decoder architecture. So the encoder is bidirectional, but the decoder is autoregressive, so only looks at the past, right? And in terms of how in BART they kind of go a little bit higher on top of BERT. They do masking of an individual token. They also mask entire spans of text. So BART is really doing a lot of noisy autoencoder stuff. So it's actually doing a lot of introducing a lot of noise in the input and trying to predict the output. So BART has a little bit of a change on how it's actually doing the training, and it's a little bit more powerful than BERT training. Okay, so you can see here token masking, just like BERT. BERT does token masking, but not just that, it also does sentence permutation. You permute a sentence and then pass it in as input and try to predict the right sentence order. So this tells you if you actually understand how to construct language. So if you can permute words in a sentence and say construct the right sentence, then that means you understand language. So by being creative in how you pass in inputs, you can train the model to be more powerful and force it to understand language better. Sentence permutation, document rotation, token deletion, you can delete things, and so on. Okay. The other thing about BART versus BERT is in BERT, you use the encoder only, and then you get a representation, and then you make prediction, right? With BART, because you have an encoder and decoder, let's say you have an input, you pass it through the encoder, you also pass it through the decoder, you get a hidden state from the decoder, and you use the state to do classification. So even though you have a decoder, you can still use a representation coming out of the decoder as your representation of the sentence, and then do sentiment classification or emotion detection. So you can still use a decoder. So BART allows you to do that. For translation, you can add an encoder that's specific to a language, say alpha, beta, gamma, delta, and then you want to translate to English. So this is a pre-trained encoder. So sorry, this is a pre-trained, but this is a randomly initialized encoder that can move from a foreign language to English language. Okay, so that's BART. I do want to do a breakout. Yeah. Let's look at this question and then we'll do a breakout on this so you can actually uh, process what we have been discussing so far and think in terms of models. So, and this can also be an interview question. Is, let's say you're tasked with building an in-email auto-completion application, which can complete partial sentences into full sentences. But also think of it in terms of query completion. So you're typing something in Google, then and then you can complete the query. So query completion in the context of search. So either of these applications. I want you to think of two things. One is, what's a traditional non-machine learning way of doing query completion? How would you do that? That's one. And the second is, how would you actually leverage a machine learning model based on what we have covered so far to do this? So in the context of search, it's called type ahead. In the context of emails, you can say it's autocomplete, right? So this is the same kind of task, but has different names. So maybe just take like 5 minutes to discuss this, and then we'll come back. Okay. Okay. Not sure. Oh. Right, I'm assigning people here. All right. So just take 5 minutes to discuss both a machine learning model and a non-machine learning model for doing this.
Hi Karthik, can you like also make me co-host for this meeting?
Done.
Okay, thank you. And also like would you like review the mini project 3 today, so like so that we can like release it? I think you're on mute.
Yeah, let's do that. Let's do that. Yeah, sure.
Got it.
Maybe we can review it after class. Just 10 minutes and then we can release it.
Sure. That would be great. Yeah, I guess as soon as the review is done, I guess I can like release it. Because like as you mentioned, I've like created the first schedule competition. I will create the second one this weekend. And yeah.
Okay, sounds good. So any thoughts anyone wants to share?
We were talking about a non-ML approach, maybe some artificial algorithm or like a star search or Dextra.
Yeah, Dijkstra.
Maybe if that can work in a way.
Yeah.
And also Sean mentioned using SQL from a database of words, if that's possible.
Yeah.
The more we get into ML, it feels like the harder it is to go backwards. Because we have all these new techniques now, so why would I try a non-ML approach when ML is very efficient?
Well, ML is good performance, but may not be very efficient, right? So especially, for instance, for search, the latency of search is very low, right? It would be in a few milliseconds or tens of milliseconds. and ML models might take hundreds of milliseconds to do inference. So in the context of search, there are head queries and tail queries. So head queries are things that you see often, and you, let's say, if you're searching, you see it a lot, right? And then you want to kind of complete the query as you're typing. That is one use case. And then there's tail queries, things that are new or you've not seen as much. And then how do you complete it? So people usually measure head query latency. They want it to be not very high. So that for majority of the queries, you cater response as well. So in that context, simpler models are better. And one of the, so that's a little bit of a context on what you were sharing. Any machine learning approaches that came up? I want to share.
Well, in the group which I was a part of, they mentioned like using like word to vec, like finding vector representations, and then further like finding similarities between them.
Yeah. That's a good one.
And in addition to that, they like also mentioned like using the count of words as a feature, because like if we wanna like suggest a word, it should probably be a commonly used word instead of the like rare words.
Makes sense.
Yeah, Yush, thank you. Yeah, you're a student now. Can you join me in my next project? I'd like to use you for the next project.
Sorry, I can't do that.
How about the other group? Anyone wants to share another group? Okay, so yeah, like we're saying, suppose you're looking at queries in search. There is head and tail, and then head is like typically things that you see a lot. The frequency is high, and this is like the tail, which is basically like the tail of something that you don't, the frequency is very low. So head queries, you typically use simple retrieval and simple models. So if you've already seen queries before, maybe you can cache it, and then you can use the cache to, give the response immediately, right? If you've seen these subqueries before, like you can produce the most likely, response for that subquery, and then as they keep typing, you will change the responses, right? So, and this is something you see in, let's say, WhatsApp. You chat on WhatsApp, and then as you keep typing, it'll keep changing what it's displaying, right? So that's type ahead for head queries. For tail queries, these are specifically things that you may have no idea about, or it's rarely seen. It might be something completely new. This is where we want a generative model. So word2vec is great, but hey guys, we have discussed transformers, so you can use GPT, right? So GPT is a very good use case for generative, like, so let's say you have a query that looks like, can you tell me about, and then what's the next one? So you pass in can you tell me about into GPT, and then you get the states, and then it'll give you the next answer, right? But again, like we said, latency might be an issue. So you have to also think about latency constraints. But any generative model for machine learning purposes is good to go for tail queries. So that understands language and can help you complete the sentence in a way that reflects language understanding. Also reflects most possible use case for the query completion. Like when I want to complete a query, this is most likely what you're going to ask. I think so. Reflecting some frequency, but also reflecting good language can help you take care of the tail query. Yeah, this is an important example, because anytime you get a task, you want to see what's the simplest solution. And just because we do machine learning doesn't mean we apply machine learning everywhere. But if there is a use case, then we apply it there, right? So here, when we break it down into head and tail, you can see where it's more applicable. All right. So with that, I think we have a lightning presentation today from Naif. So Naif, feel free to share, and we'll be glad to hear what you have to present on.
Talk about transfer learning. And I want to just emphasize on, this is an overview. I'm going to talk about the what, how, and why of transfer learning. This might remind you guys of Professor Mohan's de-stressing sessions of what, how, and why methods. So, so let's get started. Now, in transfer learning, because we're talking, well, we're learning about deep learning and pre-trained models. So it's good to understand a little bit of transfer learning, even though I still don't really fully understand it myself. But it's good to have some sort of understanding. So transfer learning is a machine learning technique where a pre-trained model is used as a starting point for a new model on a related task or data set. As you can see, this is a traditional ML approach. You have a data set, and then you do the pre-processing, you do all these different techniques on it to train the model. And then you have another data set, you have to do everything from scratch. Pre-processing, train the model. But with transfer learning, you already trained a model before from a data set. And if you have a similar task with another data set, maybe a smaller data set, you could transfer the knowledge. And this is what transfer learning is. And here is why transfer learning. So transfer learning is a powerful technique for developing machine learning models that can be trained more efficiently and effectively, especially in situations where there is limited data available. In the code, which we will see soon, this is just so an overview of what the code will show, that I will show you guys through with my notebook. A pre-trained ResNet 50 model is loaded and used as a feature extractor for a new model that is trained on the CIFAR 10 dataset. And in the notebook, I'll explain what these are. This approach allows the new model to benefit from the knowledge that the pre-trained model has gained from a large dataset, which can lead to better performance even with limited training data. By setting the trainable property of the pre-trained model to false, which you'll see in the code, the notebook will have more details about this. Only the new layers added to the model are trained, which reduces the training time and memory requirements. This approach can be particularly useful for developing optimized models for deployment on small and low-power devices, such as in TinyML applications. And next quarter, there is going to be a TinyML course with Professor Puvendran, whoever is going to take the course with me. So I think transfer learning is very important because through his syllabus, he talks a lot about that. So the data set is called CIFAR dataset, consists of 60,000, 32 by 32 color images in 10 classes. Airplane, automobile, bird, cat, deer, these are the classes. So let me show you guys the notebook. Let's see, where is it? Can everyone see the notebook, or is it sharing the presentation? Okay. So now these are the libraries to import, and of course the dataset. Now the first step is the dataset is loaded with this code from Keras, of course. Let me just, okay. And then the second part, the image data is normalized by dividing 255 to scale the pixel values to range 0s and 1. As we all know, the one hot encoded using this function. And then the third cell, a pre-trained ResNet 50 models loaded from Keras with the Keras application function, as you can see here, with the weights pre-trained on the ImageNet dataset. The include underscore top parameter here is set to false so that the pre-trained classifier layers are not included in the model. Now, fourth step is the trainable property of the base model is set to false so that the weights of the pre-trained model are frozen and only the newly added layers will be trained. Now, the fifth step is a new model is constructed by adding a global average pooling layer and a dense layer with 10 output units, one for each class. And the output, like the class that we talked before, the 10 classes. And the output of the base model is passed through these layers. The Keras model function is used to define the inputs and outputs of the model. Now then the model is compiled using the compile method with the Adam optimizer, categorical cross entropy loss function, and categorical accuracy metric. The model is then trained using the fit method with the training data, validation data, and the number of epochs specified. Now, unfortunately, I used more epochs up to 50, but the problem is that I resetted my notebook recently, unfortunately. And I lost all my epochs, so I just used 10 just for today's presentation. Unfortunately, I just restarted the runtime accidentally. So the history of the training is stored in a variable called history. And at the eighth step, the model is evaluated on the test set using the evaluate method, and the test loss and accuracy are printed to the console, as you can see. It gets better, but unfortunately, I lost my epochs, so I had to rerun it just for 10, so I can be able to have this during this presentation. Now here's some visualization, the model accuracy, as you can see, and here is the model loss. So to conclude this notebook, the ResNet 50 is a pre-trained deep convolutionary neural network that has been trained on a large data set, ImageNet. So as I explained it in the presentation, or hopefully it is explained, it has been pre-trained on a big, huge, large data set before. And what we want to do in the beginning right here is we want to use this data set, which is a smaller data set. But we don't want to build a model from scratch. So we want to find a model that is closely related to this. And luckily there is, which is the ResNet 50. And can be used as a feature extractor for other computer vision tasks, of course. Like you could use it for different tasks. This was just on the CFAR 10 dataset. By using a pre-trained model like ResNet 50 as a starting point and then fine-tuning it on a new dataset, we can take advantage of the pre-trained weights and biases to achieve better performance with less trained data and computational resources. This is called transfer learning, where we transfer the knowledge learned from one task or dataset to another related task or dataset. Now let me get to my final thoughts. Now, my final thoughts are transfer learning is a powerful tool in the field of machine learning that allows us to reuse the knowledge gained from pre-trained models to improve the performance of new models, even in cases where limited data is available. This technique is widely used in various domains such as computer vision, natural language processing, and I'm seeing it a lot in the natural language processing. Like today, we talked about BERT, BART, all of these pre-trained models. And if you have any kind of NLP project, like I'm doing right now, I'm doing an NLP project with my group, summarization and claim based on text. And we use BERT, and we use distilled BERT, which is a smaller version of BERT for this. And we also use something new called Pegasus from Microsoft, which is just another subject, and has proven to be successful in improving the accuracy and speed of machine learning models. Continued research and development of transfer learning can help us overcome challenges in developing machine learning models, such as limited data availability and computational power, and accelerate the adoption of machine learning in various fields. Now, whoever has any questions regarding this, feel free to ask Professor Mohan. He's available.
I have a question. I have a question for you, Naif. So first question is, did any of the text in your presentation come from ChatGPT?
Yes.
Because it sounded like that. Okay, great.
Yeah,
It's
I will not lie about that. ChatGPT helped me summarize my wording, made it more professional.
Tell me in 3 paragraphs what is your thoughts on transfer learning, and then it'll give you 3 paragraphs. Okay, good. Can you go back to your model in your code?
Okay.
So I want to look at the model on top of ResNet and how many layers does it have? Is it just one layer? Can you show that part? Base model. Okay, base model is what we're loading. Okay, we're not changing that. Can you go down to the model on top of it? So you have a global average pooling, so which is basically taking a bunch of pixel and then reducing the dimensionality. But then what do you do on top of that? You have a dense layer with 10 outputs. Basically, you are applying after pooling, you're doing a linear classifier.
Yeah, one with each for each class, if I'm not mistaken.
Yeah, but then aren't you supposed to apply softmax as well? How do you know this is giving you probability here? So when you apply this dense layer, you get outputs, right? But the outputs are not probabilities. Don't you want them to be probabilities? So if you apply softmax as an activation function, then you will get probabilities. And then you can compare the probabilities to your
Is that to only compare, or is it hello?
Yeah, I think yeah.
Interesting.
I think what Karthik mentioned is that like finally the sum of all the output, like sum of all the outputs should sum up to 1, and that can be mentioned as the probability. And you can like select the one with the maximum probability as the result for that given sample. And yeah, I think like using softmax at the end for classification problems.
Oh, okay. I think maybe if you look at the one below, you have from logits equals true. So maybe that's where it's taking care of that. So these are the logits before the softmax is applied. So you say use the logits. So that's why you don't have to apply softmax, because you have that set to be true. So the logits are what the input to the softmax. Okay, this is good. So that means a linear classifier on top of a max pooled version of the input that's coming through the ResNet is good enough to do a good job, right? So basically you're doing a logistic regression at the very
At the same time, the data sets, what do you call it, the CFAR data set is not that complicated. It's like a basic data set with not many complications to it.
No, but what I mean to say is if you apply logistic regression on the raw image in some way versus what you just did, there's a big difference, because the base model is already taking care of getting the right features. And once you have the right features, you can then apply a simple linear classifier, and then it does the job for you. So, right, this is great. I think the other thing I want to point out is this is a good thing that you brought up here. So you see a lot of this freezing of layers that show up in CNN, not so much in natural language processing. Like what we discussed today, the transformer model is the pre-trained version, and we don't freeze it in natural language processing training. We still fine-tune some of those weights.
Yeah, for some reason, when I was reading the documentation, you have to kind of freeze it for this task. But with NLP, what we're doing, we haven't frozen anything, because
yeah.
I don't know why specifically. Maybe you could clarify that.
No, I think maybe the amount of data you have here is not as much. And in computer vision, the models are really, really long, and we don't want to maybe mess with some of the weights. But even if you don't freeze everything, you might still only use the last but one layer or last two layers of the computer vision model, which you have an option of. I think you had an option somewhere which you set to false. If you set it to true, then you can use those last two layers. Yeah, so base model equals trainable is true, so you'd have to set that to be true. But then you can make sure the last couple of layers are in a good shape. So it turns out for images, you get really good representation, so you don't have to fine tune it. So you can just freeze the layers and then apply it to CFAR. But if you had images that are a little bit different in your new data set, you may want to train the last but one layer or last two layers. So you want to unfreeze just the last two layers of the CNN network, which is really huge.
And what do you mean by different?
Distribution is different. So let's say you have your ImageNet has a bunch of different categories, but your new task is only about birds, or it's only about fashion.
Oh, okay.
Fashion images. Everything's on fashion. So you want to fine tune a little bit of the base model for fashion so that you can make good predictions afterwards on the fashion images. Right.
You change the last layer. You have to basically drop the fully connected layers at the end because you are changing the number of classes, right?
Yeah. You drop the fully connected layer, and then you can unfreeze the last but one layer before that, and then train those, and then go ahead. Yeah, the fully connected layer at the very end. I mean, so it's a good point. You can keep.
From 1,000 to 10, right? Because I think the big data set is like 1,000 classes, and the new one is 10 classes only. So
Yeah, new one is 10 classes, but that's okay. We only care about the representation. So as long as the representation, yeah. So if the fully connected layer is dropping it, then you to discard it and keep the one before that, and use that as the starting point for your next model.
Yeah, there was a good video on YouTube from Andrew Ng, NG. He talked about the last layer, freezing the layers.
Yeah, it does depends on distribution of your new data set. If it's similar, then freeze everything. Don't take the trouble of retraining a already well-trained model, right? So it's already really well trained. You don't want to train it again with your few images that you have. But if it is different and you have significant data, then you can unfreeze and train the last layers. So those are some of the tricks in computer vision. In natural language, we almost always fine tune all the layers in the transformer as well. But this is a good presentation. Yeah. Any other questions from anyone else?
Yes, Professor Mohan is available. So
I don't have a question, but it would be great if you can like share the notebook and the slides on Discord.
okay.